All right, welcome to General Relativity and how it applies specifically to black holes. This will be an overview of some strange concepts in physics, as this is extraordinary concepts in physics. So I'm Robert Nemeroff, your lecturer here at Michigan Tech. So we're going to try to review, this whole class is reviewing some of the coolest concepts in physics we'll call it Physics X, after a famous course taught by Richard Feynman. So you can find all of these lectures online or on at this address here or through iTunes. So there should be a whole bunch of them, and this is just one. Imagine the fun you can have with the other lectures. So in general relativity has strange intervals. These things tell you how space-time curves. And these are intervals in time and space and angle. And this is sort of a sum of them all. So one of the simplest examples of general relativity and these space-time intervals was coined not by Einstein, who came up with the whole general theory, but by Schwarzschild, who came up with a whole metric. And so here you see there are things in front of the dt squared. And I guess this could have been moved over. Here's other stuff. So this is actually the solution for the way space and time curve change around a point mass. So this point mass is not spinning, it's not charged, it's not gaining or losing mass. It's just sitting there. It's the simplest case, but there's really cool stuff that happens even with this simple case. So let's review some of that. One way to picture it is through Flamm's paraboloid. So this is a way of visualizing space near a point mass. So distance is on here. If you measure a distance on this paraboloid, it would be this is a living in Euclidean flat space. So, but if you measure the space on the paraboloid, you get distances as if you were in general relativity near a black hole. So it is a way of picturing it, and if you can make it, you can actually sit there with your tape measure and measure distances that way. Let's get into some detail here of the Schwarzschild metric. What is what? So r is the radial distance from the point mass here. C, which I don't think I've used, is circumference of orbit measured at r. Tau is this one, is time measured at r, called the proper time. T, which is the coordinate distance here, is time measured at infinity. D is a differential, which is right there, this means that it involves differentiation. This is a calculus-oriented solution. You have to integrate sometimes over these to get answers. C is the speed of light, which is here. RS, there's something here. RS is the Schwarzschild radius, which I've just blotted over, which we'll get into some detail. Theta is a spherical coordinate, and phi is a spherical coordinate. Usually, for the sake of simplicity, you can just pick spherical coordinates where those don't change much. If you can get away with it, you can just have radial motion. So you can try to make those go away without a loss of understanding of what's going on. Okay, so the Schwarzschild radius, which I had mentioned before and is discussed in other lectures, is the radius essentially of the famous thing called the event horizon. So continuing what these things are, g is the gravitational constant, which is the same as a Newtonian's gravity. M is the mass of the object, which is, again, measured in Newtonian's gravity, could be measured in kilograms. C, again, is the speed of light. And the general form, a more easy form for the Schwarzschild radius, is 3 kilometers times mass of the object over the mass of the sun, which means that if you plug the mass of the sun in here, you would get mass of the sun over mass of the sun, which is 1, which means that the radius of the mass of the sun, the Schwarzschild radius, would be 3 kilometers. Now the actual radius of the sun is 700,000 kilometers. So you would have to squish the sun down to 3 kilometers in order for it to be inside its Schwarzschild radius. For the Earth, if you were strong enough, you could condense the Earth into 1 centimeter, and once you've done it that big, which might be about this big on your screen, ooh, maybe, measure it, if you could compress the Earth all into that, it would be inside its event horizon, inside its Schwarzschild radius, and act like a black hole, would be a black hole. So I guess every object you consider, even you at home, would have a black hole radius if you could push on yourself hard enough. Okay? Again, mentioned in previous lectures, classically in general relativity, it is not thought that black holes need to be defined by anything more than mass, charge, and spin. And pretty much for the Schwarzschild radius, you're really only getting into mass. So those Schwarzschild black holes, not spinning or anything, no charge, they're just mass. That's the only thing you need to define the exterior metric. It's called the no-hair theorem. You don't have to worry about it having hair or anything like that. There are other cases, even in general relativity, so I will mention them but not go into them. So the Schwarzschild radius, again, is the black hole with spin 0, charge 0. If you have no charge, but you do have spin, then you have a Kerr black hole. That is, I guess, the next most common solution of general relativity. You have things, we see things spinning all the time. Neutrons, stars spin, white dwarfs spin, the Earth spins. On a bad day, my head spins. So you would need the Kerr metric to really describe that in detail. Things in the universe are generally not charged very much because if they were charged up, if they had a tremendous negative charge, well, they'd pull in positive charge and neutralize themselves. So you don't get a lot of highly charged things in the universe, but if you did, you would get a, if the spin was 0 and it had charge, you'd get a Reasoner-Nordstrom black hole. And these things are described. General relativistic solutions exist for that. If you wanted to have the most complex mathematics, if you enjoy working with complex tensors and sophisticated differential equations, you could go after the Kerr-Newman black hole, which has charge and spin and is very messy. So I don't know anyone who really enjoys playing with that, or even it's easier just to make simple assumptions and try to understand the universe without going to that complexity. Back to the event horizon. So the event horizon is thought to be the sphere of no return. So we're going to get into trips to black holes in the very near future. If you're looking at these lectures in the future, they might already exist. So going past the Schwarzschild radius brings you to a place where you can't return. The Schwarzschild radius, however, is a sphere. It's actually not just a radius, it's a sphere around some object. And it is a sphere which is really just a coordinate singularity in general relativity. So if you were to go to that, if you looked at it from far away, you would see, we'll see next time, clocks run infinitely slowly. They just stop when they reach the event horizon. However, if you were to go yourself, every time you were to look at your wristwatch would appear the same. If you're outside the Schwarzschild radius, whether you're at the Schwarzschild radius, whether you're inside the Schwarzschild radius, your wristwatch looks like it's running at the same speed. Now, if it's a small black hole, like even a solar mass black hole or certainly a Earth mass black hole, you'd be ripped to shreds. But if it's a very big mass black hole, like the mass of a center of a galaxy or something like that, then you might not even know that you're passing the event horizon. There might be no indication. Once you're past the event horizon, though, you can't go back out. It is considered that one way of thinking about this is that time and space might be considered to be reversed. You're only allowed to move toward the center, assuming you're in assuming all the mass is condensed at the center. Okay, spinning black holes become much more sophisticated. They have something called an ergosphere. So here's a picture. Here's the classical event horizon if it wasn't rotating. But since it is rotating, you have something called an ergosphere. So inside, the black hole is thought to, one could track, if one could track the spinning speeds there, it would be considered faster than the speed of light. Outside, you would be frame dragged with the spinning. This is true of actually any spinning object. You're slightly pulled with it when you go near it, which is a general relativistic effect called frame dragging, which means that a person near the black hole would feel slightly less rotation than they might have thought they would have felt if they came in from infinity. It is possible to escape from the ergosphere of a black hole, of a spinning black hole. There are other processes. Many physicists have looked at this in some detail, and there are ways through Penrose process and Blanford-Zanyek process, I don't know if I'm pronouncing that right, where you could steal energy from rotating black holes. Basically, you spin, the black hole has a lot of energy in its spin. You could steal that energy in some way, cause the black hole to spin less rapidly, and you could possibly power your extraterrestrial civilization once you become emperor. This people have suggested these things as powering quasars. Okay, as alluded to in other lectures, particularly the black hole thermodynamics evaporation lecture, Oh, I'm sorry, this went in front. I actually tried to change that. Black holes are now thought, general relativity doesn't allow this, but when mapping some relatively straightforward concepts of quantum mechanics onto general relativity, you can get things like black holes evaporating. They actually emit particles. And the surface area that they emit the particles is essentially the black hole event horizon surface area, and that's proportional to its temperature. High mass black holes, like galaxy mass black holes, they would be very cold. The amount of energy density coming out of a black hole that massive would be very low. However, low mass black holes would be very hot. And in fact, as a black hole becomes very low mass, below Earth mass, down to asteroid masses and less, it would actually explode. It would be so hot that it would explode and give away all its mass into particles that would come back into the universe. So this brings up the question, which I'm going to attack again. It was in another lecture, but I'm going to bring it from a slightly different angle this time. Can you store information in a black hole? And this is actually a fun topic in a slightly different context for when I was in graduate school. Let's say you borrow your king's favorite flash drive. We just called it a disk drive, only to mistakenly drop it into a black hole. Now, you see the drive hovering just outside the event horizon, and the king's going to want it back. So, can you go get it? Yes. One answer. Just go get it. You must. You dropped the flash drive. You made a mistake. Go get it. No, don't go get it. Black hole's going to get it. There's nothing good can happen there. Or might the king be appeased by a nice fruit basket? Then you won't have to even think about this. So the answer is no. Actually, well, you shouldn't go after it unless you can grab it right away. Because after a small time interval, which depends on exactly how far away you are and things like that, the only thing that survives effectively is the image. You cannot go grab it back. So no matter how much you spend on rocket ships to go shooting in to try to get that flash drive back, you will never get there and get it and grab it and be able to pull it back before it passes the event horizon. It's impossible. So you'll be seeing the image though. Lowering yourself onto the black hole on a thick rope will only lead to the rope breaking. It's a little bit like those poles in the pole in the barn special relativity thing and the rotating pole, the twirling pole. You get into strength of argument, strength of objects arguments as to how strong things can be. Okay, so the jump drive is gone. However, maybe you can get the information back from it. If you could just copy that onto another drive and avoid having to buy the king of nice fruit baskets, can you do this? If you can see the drive, you can see the information on it so you can get it back. No, the drive is irretrievably lost. I don't know, and I've learned to live with uncertainty would be the third one. Got it? Here we go. No. We don't know if you can get information back from a black hole. Even if you can see the drive, you might be able to get some information from it, but it might be gone. And so the black hole evaporation has that more. I'll review some of that here. If you can't get it back, it preserves the no-hair theorem, which is straightly GR. There are other ways the information could get out. It could leak. It could end up in a Planck-sized dense remnant. There are correlations that could occur. Okay, so I got to touch quickly on white holes, which are just like black holes, except they emit stuff. They're a time-reverse solution of black holes. I don't know many people who deal with them. There are some people think that white holes are just black holes. Wormholes are more interesting. These are known as Einstein-Rosen bridges. Their practical existence is controversial because it's possible, in theory, to go through a black hole and come out a white hole. And the thing together would be known as a wormhole, but you would need negative mass energy to keep the throat open. So what's that? We'll go into that in other lectures, but this stuff might actually be common in dark energy and cosmic strings. If you could do this, though, it might raise some interesting problems. You might allow faster than light communication, and it might allow time travel, which is not strictly forbidden in general relativity, but not thought to occur. So the last thing I'll touch on is the twin paradox. So you can have a twin paradox near a black hole just like special relativity has a twin paradox with fast speeds. So if one twin leaves and hangs out near a black hole and the other twin stays home in a normal place, when the black hole twin returns, they can find the other twin, which used to be exactly their same age, as old and gray. And this in itself does not allow you to travel to your own past, but it allows time travel to the future in some way. And with that, I'll leave you to next time and more fun lectures. Bye. All right, welcome to General Relativity and how it applies specifically to black holes. This will be an overview of some strange concepts in physics, as this is extraordinary concepts in physics, and this is sort of a sum of them all. So one of the simplest examples of general relativity and these space-time intervals was coined by, not by Einstein, that came up with the whole general theory, but by Schwarzschild, who came up with a whole metric. And so here you see there are things in front of the dt squared. So I'm Robert Nemeroff, your lecturer here at Michigan Tech. So we're going to try to review, this whole class is reviewing some of the coolest concepts in physics we'll call it Physics X, after a famous course taught by Richard Feynman. So you can find all of these lectures online or on at this address here or through iTunes. So there should be a whole bunch of them, and this is just one. Imagine the fun you can have with the other lectures. So in general relativity, general relativity has strange intervals. These things tell you how space-time curves. And these are intervals in time and space and angle. And I guess this could have been moved over. Here's other stuff. So this is actually the solution for the way space and time curve change around a point mass. So this point mass is not spinning, it's not charged, it's not gaining or